Welcome back to the Deep Dive, the place where we cut through the noise and complexity to give you the knowledge that truly matters. When we usually talk about the AI revolution, um, the focus is almost always on the gargantuan effort of building these models. The billion-dollar training runs, the race for the biggest data centers, months of just intense computation. But today, we're shifting gears. We're focusing entirely on where the real work and honestly, the real strategic and economic challenge lies. We're talking about the moment of truth, the inference phase.
Right, that's where the model is actually deployed, doing its job, serving users.
Exactly. And this focus, it's driven by a pretty stark economic reality we found in our sources.
Yeah.
Training, yeah, it's the big upfront investment, the capital cost.
But inference, that completely dominates the operational costs. By most estimates, we're talking 90% of a modern AI model's total lifecycle spending.
90%. I
Yeah.
mean, that figure is just staggering, especially when you think about the headlines, the huge price tags for training something like GPT-4.
It really is.
So our mission in this deep dive is to really understand the strategic fundamentals of AI inference. We'll dig into that massive operational cost, the technical bottlenecks, why is speed so hard, and, the brilliant, sometimes lightning-fast optimizations engineers are using right now.
Yeah, we're going to cover quite a bit. Everything from foundational strategies, things like quantization, tensor parallelism, right up to some really advanced tricks that are changing how LLMs generate text. We'll look closely at speculative decoding and the adaptive magic of something called activated low-rank adaptation, or ALoRA.
Okay, so the big question then, the one driving this whole conversation. If training costs, say, hundreds of millions up front, why on earth does inference end up dominating the operational side? And crucially, how are engineers actually winning this fight against complexity and speed to give you, the user, those near-instant responses? All right, let's start simple. Let's draw a really clear line between the two main phases of a model's life. Phase one, training. Can you recap that quickly?
Sure. Training is basically the learning phase. The model gets fed just vast amounts of data, and through trillions, literally trillions of calculations, it starts analyzing relationships, finding patterns, figuring out the structure in that data.
It's learning the rules of the game, so to speak.
It's constantly adjusting itself until it can accurately predict, say, the next word in a sentence or classify an image correctly. The end result, a set of encoded knowledge stored in what we call the model's weights. It's like the AI's collective memory.
Okay, learned memory. Phase two, inference. This is where, as I said, the rubber meets the road.
Right. Inference is the application phase. The model's trained, its weights are frozen, it's deployed. Now it takes real-time, unseen input, maybe your query to a chatbot, a new picture you upload, an incoming financial transaction.
Stuff it hasn't explicitly learned from.
Precisely. And it uses those stored weights, those learned patterns, to make a prediction or deliver some kind of actionable output. It's generalizing from its training to handle new situations, moving from learning to doing.
Okay, now let's tackle that 90% number head on. We hear about these billion-dollar training runs. It really sounds like that upfront cost is the biggest hurdle. How is it even possible that the day-to-day running, the inference, eats up 90% of the cost over the long haul?
Well, it comes down to a classic business distinction, right? Capital expenditure versus operational expenditure, CapEx versus OpEx. Training is CapEx. It's that massive, intense, often one-time investment to build the asset. You buy the GPUs, you run them flat out for maybe 6 months, then boom, the training's done, the asset is built.
But then the meter starts running differently.
Exactly. Once that asset is deployed, the operational cost kicks in. Inference is OpEx, and OpEx, well, it scales directly with usage.
Ah, okay. That's the key. Training happens once, maybe a few times for updates.
Right. But inference, that happens every single time a user interacts with the model. Every single time. If you've got a popular chatbot out there, you could be handling millions, maybe billions of requests every single day. And each request, no matter how simple it seems to the user, requires a calculation using potentially billions of those stored parameters. That recurring cost, multiplied by that massive scale, just quickly dwarfs the initial training investment, usually within, say, 3 to 5 years.
So the training cost might be this spectacular, mountain of cash up front, but the inference cost is like this constant, powerful river of money flowing out day after day.
That's a really good way to put it. And it's not just economic, the implications are ecological too. Our sources point out that the majority of AI's energy footprint, its CO2 emissions, actually comes from serving models in inference mode.
Not the big training runs we hear about.
Not primarily, no. Those are intense but short-lived, relatively speaking. It's the sheer volume, the constant 247 execution of inference tasks across the globe that really adds up.
Okay, let's zoom in a bit. What makes inference so expensive beyond just, lots of queries? You mentioned 4 key cost factors in our sources. First one, obviously, is operational scaling.
Yeah, the sheer volume we just talked about. Every single execution draws power. Servers have to be on, ready, waiting 24/7, even when usage dips. It's the constant background hum of the AI infrastructure.
Makes sense. Second is the need for speed. This sounds like just, user expectation. I want my answer now. But technically, that demand forces the most expensive choices, right?
Oh, absolutely critical. Think about applications like self-driving cars or real-time voice assistants or even high-frequency trading. You simply cannot tolerate delays. Latency has to be minimal.
Milliseconds matter.
Exactly. And achieving that ultra-low latency, it demands dedicated, powerful, top-of-the-line hardware. We're talking specialized GPUs, maybe even custom-built chips, ASICs. These things are incredibly expensive to buy, to house, and critically to power. They jack up the baseline operating cost for every single calculation.
So it's not just running the math, it's running it on a Formula One car instead of a family sedan, just to get the answer back instantly.
That's a fair analogy, yeah. The third factor is model complexity. Even if my question is simple, like what's the capital of France? The model itself might be huge.
Those LLMs with tens, hundreds of billions of parameters.
Right. So even for a simple query, every forward pass through that model involves moving and crunching just immense amounts of data. The complexity is baked right into the size of those weight matrices that have to be accessed every single time.
And finally, number 4, the infrastructure. The stuff we don't often see.
Yeah, the relentless ongoing costs. Maintaining data centers isn't cheap. You've got cooling for these massive GPU clusters. They generate incredible heat. You need redundant power supplies. You need specialized, super fast, low latency networks to shuttle data between you, the user, and the server farm and back again really, really quickly.
Wow, that's up.
It all compounds. And this is why optimization is key. If engineers can shave off milliseconds, they save kilowatts. If they save kilowatts across billions of inferences, they save millions in OpEx over a year.
Okay, to make this less abstract, let's use that spam detector analogy you mentioned. It really shows a whole journey from the raw AI output to an action that actually affects, say, your inbox.
Right, perfect example. Start with training. The model sees millions of emails already labeled spam or not spam. It learns the features, maybe weird keywords, dodgy sender addresses, too many exclamation points, you know the type.
Yep.
That knowledge gets encoded into its weights. Now, inference time. A brand new email hits your inbox.
Unseen by the model before.
Correct. The trained model processes this new email using its learned weights. And the critical output here isn't a final yes or no, it's a probability score. The model might say, okay, based on what I've learned, there's a 95% probability this email is spam.
But that 95%, it doesn't actually do anything on its own, right? It's just a number.
Exactly. That's the crucial link often missed. The raw output is just data until it's connected to an actionable business rule, a rule defined by humans, by the system designers. Without that rule, 95% is meaningless information.
So we need to tell the system what to do with that score.
Right. We define a rule set. Rule 1 might be, if the spam probability is 90% or higher, automatically move it to the spam folder. Don't even bother the user. That's a high confidence action.
Okay, but what if the model's less sure? Say it outputs 60% probability.
Then you need a different rule. Maybe rule 2 is, if the probability is between, say, 50% and 89%, keep it in the inbox, but flag it with a warning. Let the user decide. The action changes based on the model's confidence and the risk you're willing to take.
Got it.
And that entire pipeline, receiving the email, running the model, getting the score, applying the business rule, executing the action, like moving the email, that whole sequence is the inference process. And for a good user experience, it has to happen almost instantly.
That really clarifies the stakes. Optimizing inference isn't just some academic exercise for speed. It's about cutting the cost of every single decision that AI makes billions of times a day, worldwide. Okay, so that relentless pressure to cut those massive recurring OpEx costs, that's really the engine driving all these optimization strategies we're seeing. Our sources really emphasize you can't just fix one thing. You need improvements across the board, hardware, software, and the bits in between.
Absolutely. You have to tackle the complexity of the whole computational graph. That's basically the network of steps the model takes right from the foundation up.
Let's start with the hardware layer then, specialized AI accelerators. How are these fundamentally different from, say, the CPU or even the GPU in my gaming rig?
Well, traditional CPUs and even general-purpose GPUs are designed to be flexible, right? They handle graphics, physics calculations, spreadsheets, all sorts of things. AI accelerators, things like Google's TPUs or other specialized ASICs, are different. They are purpose-built, almost obsessively optimized, for one thing, the specific kind of math underlying deep learning.
Which is mostly matrix multiplication.
Primarily, yeah. Matrix multiplications and convolutions. By stripping away all the general purpose flexibility, these chips achieve huge gains in speed and, critically, energy efficiency, but only for those specific AI tasks.
So same power input, much more AI number crunching output.
Exactly. That directly tackles the cost linked to speed and energy consumption we talked about.
Okay, moving down the stack to the software layer. Model compression. The idea here is to make the model smaller without losing its smarts. First up, pruning. What's that involve?
Pruning is like, well, selectively removing connections in the neural network.
Huh.
Imagine this vast web. Some connections, represented by weights, are super important for the final answer. Others have weights very close to zero. They barely contribute anything.
Dead weight, basically.
Pretty much. Pruning algorithms identify and permanently snip away those low contribution weights. This makes the model file smaller, which saves memory, and reduces the number of calculations needed for each inference pass.
Sounds great, but is it tricky to get right? I imagine you could prune away something important by accident.
It can be. The challenge is how you prune. If you just randomly remove individual weights here and there, that's called unstructured pruning. The resulting pattern of quantization is a fundamental lever for cost savings. Historically, models use 32-bit floating point numbers, FP32, for really high mathematical precision. Quantization reduces that bit depth, often down to 16-bit floats, FP16 or BF16, or even 8-bit integers, INT8, and sometimes now even 4-bit integers.
And that helps out.
It's transformative for, I'd say, three main reasons. First, memory footprint. An INT8 model takes up only 1/4 of the memory space of its FP32 counterpart.
Wow, 4 times smaller.
Yeah, this means you can fit much larger models onto the GPU's own super-fast memory, the HBM or high bandwidth memory. And that HBM, that's the most precious, expensive, and limited resource on the chip. Fitting your model there is key.
So if my top-end GPU has, say, 80 gigs of HBM, fitting a 40-gig INT8 model is way easier than trying to cram in a 160-gig FP32 version.
Exactly. Big operational advantage. Second reason, reduced memory bandwidth usage. Running inference constantly involves fetching model weights from memory to the compute units. Lower bit depth means you're physically moving less data around for every single calculation.
And moving data is slow and power-hungry.
It's often the biggest bottleneck, especially for large models. Reducing that memory traffic is crucial. And the third reason, specialized hardware speed.
Ah, like those AI accelerators we mentioned.
Precisely. Many modern GPUs and accelerators have dedicated compute units, specialized engines, built specifically for INT8 or even INT4 math. These cores are hardwired to blast through low-precision calculations much, much faster than they can handle high-precision FP32 math. So, by quantizing your model, you unlock this specialized hardware acceleration.
Which means more throughput, more answers per second.
Dramatically more throughput, which directly lowers your cost per query. It's a huge win.
Okay, so we've got faster chips, smaller models. Now, the middleware, the bridge between hardware and software. Let's talk about graph fusion. Sounds technical.
It is a bit, but the concept is simple. Remember the computational graph. All the steps the model takes. Often, what looks like one high-level step, say calculating an attention score, is actually broken down into many smaller individual operations or kernels. Each of those tiny steps might require the CPU to tell the GPU what to do. That's a kernel launch, and maybe data gets shuffled back and forth. These communication cycles, these round trips between CPU and GPU, they add up. They cost time, they add overhead.
So graph fusion tries to cut down on that chatter.
Exactly. It smartly looks at the graph and identifies sequences of these small adjacent operations that can be mathematically combined or fused into a single, larger, custom-built kernel. So instead of launching, say, 3 separate instructions and maybe making 3 memory trips, you launch just one optimized, fused kernel.
Fewer interruptions, smoother flow.
Right. It minimizes the latency from all that instruction overhead and memory back and forth, leads to significantly faster execution of the whole inference pass.
Okay, one more foundational strategy, especially vital for the really enormous LLMs. Tensor parallelism. You mentioned earlier a huge model, maybe 70 billion parameters, might need 150 gigs of memory, but a single GPU only has 80 gigs. How does tensor parallelism solve that physical limitation?
Yeah, this is essential for the giants. It's basically clever workload splitting focused on those massive matrix multiplications that are core to these models. The model's parameters, the tensors, are just too big for one GPU's memory. So we don't just load different layers onto different GPUs, we split the actual computation within a layer.
How did that work? Can you give an analogy?
Sure. Imagine you have this absolutely enormous spreadsheet that's your weight matrix, and you need to multiply it by a row of incoming data that's your input vector. It's too big for one person or one GPU to handle.
Okay.
With tensor parallelism, we slice that giant spreadsheet, maybe horizontally, maybe vertically, depending on the type. We give half to GPU 1 and half to GPU 2. They both get the same incoming row of data.
Ah, so they work on the same input, but only using their piece of the huge parameter matrix.
Exactly. They calculate their partial results simultaneously in parallel. Then there's a quick communication step where they exchange or combine those partial results to get the final complete output for that layer. That output then gets passed to the next layer, which might also be split across the GPUs.
So it spreads both the calculation work and the memory load.
Critically, yes. It distributes the memory footprint across multiple GPUs. Without tensor parallelism, any model bigger than a single GPU's memory would be practically impossible, or at least economically infeasible, to deploy for inference. It's fundamental tech for today's large models.
Okay, that groundwork sets us up perfectly for our first really deep dive into optimization, focusing squarely on the latency problem, the sheer slowness in large language models. When an LLM generates text, that standard vanilla process, it's inherently sequential and slow. Let's unpack that first.
Right. The core issue is the autoregressive nature. It generates text one token, essentially one word or part of a word, at a time. It operates in this tight loop. Step 1, take the current sequence of text, the prompt, plus whatever it's generated so far. Step 2, run a full, computationally expensive forward pass through the entire massive network using that sequence as input. Billions of calculations. Step 3, the output of that pass is a probability distribution over every single word the model knows.
A prediction of what word should come next.
Exactly. Step 4, it samples or picks just one single token from that probability distribution based on those scores. Step 5, it appends that one token to the sequence, and then the whole loop starts over again for the very next token.
One token per massive calculation cycle.
Yeah.
So if I ask it for, I don't know, a 500-word blog post, I'm forcing it to run that entire expensive forward pass 500 separate times.
Pretty much, yeah. Maybe slightly fewer depending on tokenization, but essentially, yes, that sequential one token at a time process is the fundamental speed bottleneck we need to break.
And speculative decoding is presented in our sources as a major breakthrough for cracking this exact problem. It uses a draft and verify approach.
Exactly. It's a really clever strategy. It doesn't get rid of the sequential loop entirely, but it uses parallelism within each step of the loop to essentially guess ahead.
And the trick involves using two models working in tandem.
That's right. You introduce a draft model. This is a much smaller, faster, cheaper model to run maybe just 3 billion parameters compared to the main one. Its job is purely high-speed speculation, making quick guesses.
Okay, the speedy guesser.
And then you have the target model. This is your big, accurate, high-quality LLM, say, 70 billion parameters. Its job isn't to generate step-by-step anymore, but to efficiently verify the speculations made by the little guy.
The economic logic seems clear. Use the cheap, fast model most of the time if its guesses are good, and only bring in the expensive, slow, accurate model to check the work and correct mistakes.
That's the core idea, and the goal is ambitious. Generate maybe 2, 3, even 4 final high-quality tokens in roughly the same amount of time it normally takes the big target model to generate just one.
Okay, let's walk through the 3 key steps our sources outline. Step 1, token speculation, the draft.
Right. The small, fast draft model gets the current context. Let's use the example. The capital of France is. It then starts generating quickly, autoaggressively. It might draft, say, K44 tokens ahead. Let's imagine it guesses. Paris, a beautiful city.
Okay, plausible guess.
As it generates each of those 4 tokens, Paris, say it's a beautiful city, it also records its own internal confidence score for each guess. We call this the draft probability, DPDT. This whole drafting process is super fast because the model is tiny.
Right. Now, step 2, parallel verification,
Yeah,
the check. This sounds like where the magic happens for efficiency.
This is the crucial bit. Instead of the big, slow target model calculating token by token, We feed it the entire extended sequence all at once. The capital of France is Paris, a beautiful city. The target model performs only one single expensive forward pass on this whole thing.
Just one pass, even though there are 4 new tokens.
Yes. And in that one pass, it calculates its own high-quality probability score, the target probability, TP-AQRDs for every single token in that sequence. That includes the 4 tokens the draft model guessed, plus it predicts the probability distribution for the token that should come next, the K plus $in token.
Wow, okay, so it verifies all 4 guesses and predicts the next step, all simultaneously in one go. That skips 3 full forward passes of the big model right there.
Exactly. Huge computational saving. Now, step 3. Rejection sampling. This is the quality control step, right? Making sure we don't just accept potentially bad guesses from the small model. Precisely. Rejection sampling is the mechanism that mathematically guarantees the final output sequence is statistically identical to what the large, accurate target model would have generated if it had done it the slow, sequential way.
I just do that.
It iterates through the sequence of drafted tokens one by one, starting with the first guess, Paris. For each token, it compares the target model's probability, TP-cell for that token, with the draft model's probability for the same token.
And there's a rule for acceptance.
Yes. A drafted token is accepted only if the target model's probability is greater than or equal to the draft model's probability. TPDT-Fi. Basically, the big model has to be at least as confident as the small model was about that specific guess.
What if the draft model was overconfident? It guessed city with high probability, high DP-pi, but the target model thinks city is actually unlikely there.
Low TP-pi.
That's where the rejection happens. If TP, the token is rejected, and this is critical, the process stops immediately at the first rejection.
So if city gets rejected, any tokens the draft model guessed after city are also thrown out.
Correct. Even if they might have happened to be correct later on. The system makes a clean break at the first point of deviation, where the target model disagrees strongly enough with the draft model's confidence. It doesn't trust anything the draft model said after that point.
Okay, makes sense. So what happens after a rejection? The system then uses the high-quality probability distribution calculated by the target model at the point just before the rejection. So after accepting Paris, a beautiful, it uses the target model's probabilities for the next token to sample a brand new correct token. Maybe it samples infamous. This newly sampled token is guaranteed to match the statistical preference of the big 70 billion parameter model.
So let's recap that example. Draft model guesses Paris, a beautiful city. Target model verifies Paris is accepted. TPA accepted, beautiful accepted. But city is rejected. TPBPE, the system stops, uses the target model's distribution after beautiful, and samples and.
Right. So in that single cycle, which involved only one forward pass of the expensive target model, we potentially accepted, say, 4 tokens, Paris a beautiful, and generated one new one, and we got 5 high-quality tokens for the price of 1 calculation.
That's where the 2x, 3x, maybe even more speed up comes from.
Exactly. And that speed up translates directly into lower latency for you. The AI feels much more responsive. And crucially for the providers, it means a massive reduction in the operational cost per generated token because you're doing maybe 4 times the useful work for the energy cost of 1 standard cycle.
And that guarantee you mentioned, the final output being statistically identical to the slow, high-quality model, that's absolutely key. It means you get the speed boost without sacrificing the accuracy or coherence that the big model provides.
Absolutely. That quality guarantee is what makes speculative decoding such a powerful and widely adopted technique now.
Okay, shifting gears a bit now. We've talked about speeding up general text generation. But what about making AI more specialized and adaptable? This leads us to the next strategic challenge: creating AI that can handle multiple distinct tasks effectively without getting confused. Our sources talk about avoiding cross-chatter.
Right. In complex systems, maybe like a mixture of experts model or just one large model trying to be good at everything from writing poetry to analyzing medical data, you risk knowledge dilution or interference between tasks. The ultimate goal, the vision here, is for truly adaptive AI.
What does that look like in practice?
Imagine a single, powerful, foundational LLM that can instantly switch its specialized skill set on the fly. One moment, it's acting like a meticulous legal assistant, understanding complex contracts. The next moment, maybe triggered by the context, it instantly becomes a highly focused scientific calculator handling complex notation.
And it does this without needing downtime, without having to reload gigabytes of data.
Exactly. Hot swapping skills instantly. The analogy our sources use is quite good. Think of the base LLM as your game console, always powered on. Each specialized skill, legal analysis, coding, scientific notation, is like a separate game cartridge or module, an adapter that you can just instantly plug in and activate.
Okay, that's a compelling vision. To understand how we can possibly plug in these skills, we need to grasp the core mechanism that actually allows LLMs to understand context and meaning in the first place, the attention mechanism.
Yeah, attention is really the heart of the transformer architecture, which underlies almost all modern LLMs. It's the mechanism the model uses to figure out which parts of the input text are most important or relevant for predicting the next word, or for understanding the overall meaning. It assigns importance weights based on context.
And this relies on the interplay of those three famous vectors: query, Q, key K, and value V. Can you break down what Q, K, and V represent in simple terms?
Sure, let's take a sentence like, the bank robber parked his car by the riverbank. The model needs to figure out which meaning of bank is relevant at each point.
Okay.
Let's focus on the second bank. The query Q vector essentially represents that word bank, asking the rest of the sentence. What context clues are relevant to understanding me right now?
It's looking for information.
Right. The key K vectors are like labels for every other word in the sentence. The word river has a key vector that essentially says, I am river, I offer context related to geography, water, etc. The word robber has a key saying, I am robber, I offer context related to crime, money, etc.
So the query compares itself to all the keys.
Exactly. The query for the second bank compares itself mathematically, using a dot product, to all the key vectors. It will find a strong match, a high score, with the key for river. It won't match well with robber or car.
And the value V.
The value vector for each word holds the actual substance, the semantic meaning or information content of that word. So once the query bank finds a high score with the key, river, it uses that high score turned into an attention weight via softmax to pull information primarily from the value vector associated with river.
Ah, so the high score for river tells it to grab the geographical feature meaning from river's value, effectively defining the second bank as the edge of the river.
Precisely. That weighted sum of the value vectors, based on the query key scores, becomes the new, contextually informed representation of that word bank. And this happens for every word in the sequence.
It doesn't just do this once, right? There's multi-head attention.
Right. The model performs this entire QKV calculation multiple times in parallel, with different sets of QKV projections. These are the heads. This allows it to simultaneously focus on different kinds of relationships. One head might track grammatical dependencies, another might focus on semantic similarity, another might track pronoun references across long distances.
It's a really powerful mechanism for understanding context, but it leads directly to what you call the single biggest performance killer in inference: quadratic complexity.
Unfortunately, yes. That self-attention calculation, where every token's query has to compare against every other token's key, has a computational complexity of 1 NDLED another. N is the sequence length, number of tokens. D is the model's internal dimension size. The killer part is the 2 and dollar.
Meaning the computation scales with the square of the sequence length?
Exactly. If you double the length of your input text, say from 1,000 tokens to 2,000 tokens, the amount of computation required for the attention calculation doesn't just double, it quadruples. If you triple the length, it goes up by a factor of 9.
That sounds unsustainable, especially for use cases like summarizing a whole book or having a really long conversation with a chatbot.
It is. It creates an enormous computational bottleneck, yes. But maybe even more critically, it creates a massive memory bandwidth bottleneck. For every new token you generate, its query needs to compare against the keys of all the tokens that came before it. As the sequence gets longer, the amount of key data you need to fetch from the GPU's main memory, which is relatively slow, into its fast on-chip memory for the comparison just explodes.
The sheer volume of data movement becomes the limiting factor.
That's often the case. It drives latency up and throughput down, making very long context prohibitively expensive to serve.
Okay, so engineers obviously needed ways to fight back against this dollar beast. Let's talk about the strategies. First, a crucial memory management technique: KV caching.
This is absolutely fundamental for making LLMs usable in conversation. The key insight is, once you've calculated the key K and value V vectors for a token in the past sequence, they never change. They depend only on the input tokens, not the ones generated later.
So recalculating them every single time you generate a new token is incredibly wasteful.
Totally redundant. KV caching simply stores the calculated K and V vectors for all the preceding tokens in a dedicated cache, usually in the GPU's fast HBM memory. When the model needs to generate the next token, token n plus 1, it only calculates the new query vector for that token. It then compares this new query against all the keys from token 1 to n that are already stored in the KV cache.
It avoids recalculating the entire attention matrix for the past history. That must save a ton of computation.
It saves immense compute, yes. But just as importantly, it manages that memory bandwidth problem. You're not constantly refetching old K and V data from main memory. However, it introduces its own challenge. The KV cache itself takes up space in that precious limited HBM. So efficiently managing the size of the KV cache becomes the new bottleneck for serving models with very long context windows.
Right. Next, optimization targeting that memory traffic problem. Flash attention. This sounds fast.
It is. Flash attention is a highly optimized algorithm, not a change to the model structure itself, but a smarter way to implement the attention calculation, specifically designed for modern GPUs. Its main goal is to drastically reduce the amount of reading and writing to the GPU's main slower HBM memory during the attention computation.
How does it do that?
It cleverly reorders the mathematical steps. It breaks the calculation into smaller blocks and uses techniques like tiling and recomputation to keep as much of the intermediate data as possible, things like the attention scores before the final weighting within the GPU's super-fast on-chip SRAM memory.
Avoids those slow round trips to the main HBM.
Precisely. By minimizing those costly memory I/O operations, flash attention achieves massive speedups and allows GPUs to sustain much higher throughput, tokens per second, especially when dealing with the long sequences that would normally be choked by memory bandwidth limitations.
Okay, and then there are even more aggressive approaches like sparse and linear attention that sort of challenge the core idea of full attention.
Yeah, these are approximations. They start from the premise that maybe every token doesn't really need to attend to every single other token in a very long sequence. Perhaps only local context or interaction with a few key global tokens is sufficient.
So they limit the connections.
Exactly. They introduce sparsity patterns. Maybe a token only attends to its nearest neighbors, or uses clever hashing tricks, or employs other methods to reduce the number of query key comparisons. The goal is to break that dollar complexity and get closer to linear scaling. This allows for potentially massive context links, maybe at the cost of a small potential hit to accuracy on tasks that truly require very long-range dependencies.
Got it. Okay, all these optimizations, KV caching, flash attention, fighting 2, they lay the groundwork for enabling that dynamic skill system we talked about. Which brings us to activated LoRa. ALoRA. First, can you remind us what plain LoRa is?
Right. LoRa stands for low rank adaptation. It's a very popular technique for parameter efficient fine-tuning, or PEF. The core idea is incredibly powerful. You take a massive pre-trained foundational LLM, maybe 70 billion parameters, which already has broad knowledge. You want to teach it a new specific skill, say, answering questions about a specific company's internal documentation.
But you don't want to retrain the whole 70 billion parameter beast, which would be hugely expensive.
Exactly. With LoRa, you freeze the weights of the entire original model. All those billions of parameters remain untouched. Then you inject tiny new trainable matrices or to specific parts of the model, typically within the attention blocks, modifying the projections that create the Q, K, and V vectors.
So you only train these tiny adapter layers.
Yes. These adapters might only contain, say, 0.01% of the total parameters of the original model. You train only these small adapters on your specific task data, the company documents. Because the original model's knowledge is still there, the adapters learn very quickly how to steer that knowledge towards the new task.
So you get specialization expertise in company docs while training maybe 10,000 times fewer parameters than a full fine-tune. Huge savings in time and cost.
Massive savings, that's standard LoRa. Now, what makes activated LoRa special and enables that instant hot swapping of skills?
Yeah, what's the activated part do? Normally, if I switch from a LoRa adapter for legal to one for coding, wouldn't the system get confused about the conversation history that was generated using the legal adapter?
That's precisely the problem ALoRA solves. Normally, yes, switching adapters midstream would be problematic. You'd likely have to clear the session history, represented by the KB cache, because that cache was built using the context process through the previous adapter's modified QKV projections. Recalculating the whole history with the new adapter would cause a significant pause, a big latency spike.
Okay, so how does ALoRA avoid that recalculation?
It cleverly leverages the KV cache we discussed earlier, which was designed to fight the dollar problem. Remember, the K and V vectors stored in the cache are derived primarily from the outputs of the frozen foundational base model layers before the tiny LoRa adapters modify the final QKV projections for the attention calculation itself.
Ah, so the historical context stored in the KV cache is mostly independent of which adapter was active when it was generated.
Largely, yes. The core context representation comes from the big, unchanging base model. When you activate a new ALoRA adapter, it only starts influencing the new QKV calculations for the next token to be generated, and all subsequent tokens. It doesn't invalidate the K and V values already stored in the cache from the past conversation history.
That is really elegant.
Yeah.
Means the base model provides the stable memory of the conversation via the KV cache,
Yeah.
and the ALoRA adapter instantly provides the specialized lens or skill for processing the next step without needing to reprocess the entire past.
Exactly. You can switch from a legal analysis adapter to a Python coding adapter almost instantaneously mid-conversation without that jarring pause or the need to recalculate potentially thousands of past tokens.
So ALoRA effectively turns specialized knowledge into a lightweight plug-and-play component that can be activated or deactivated on demand, leveraging the existing optimized infrastructure like KV caching.
That's the beauty of it. It makes the vision of highly adaptable, multi-skilled AI systems much more practical and economically feasible for complex, real-world deployments.
Hashtag outro. Wow. Okay, this deep dive really underscores that efficiency isn't just a nice-to-have in AI. It's absolutely fundamental. It's the strategic resource. Let's try to quickly summarize the key takeaways from our journey today. 1. Forget the training hype for a second. Inference is the dominant ongoing cost of AI. It easily accounts for 90% or more of a model's operational lifespan, its energy use, its carbon footprint. OpEx is the real battleground here.
2. To fight the inherent slowness of generating text token by token, engineers use really clever architectural tricks like speculative decoding. Using a small, fast draft model to guess ahead and a large model to verify in parallel gives us huge speedups, 2x, 3x, maybe more crucially, without losing the quality of the big model.
Right. And 3, that fundamental bottleneck of quadratic complexity in the attention mechanism, the Dunham-Tooth problem, is being tackled head-on. Memory optimizations like KV caching and super-efficient algorithms like flash attention are crucial for handling long sequences.
hmm And those very optimizations, particularly KV caching, are what then enable advanced capabilities like the dynamic instant skill specialization we see with ALoRA.
Yeah.
Tiny, efficient adapters can be hot swapped on top of a frozen base model, giving us adaptable AI.
What really stands out to me listening back is how interconnected all these optimizations are.
Absolutely. Every technique we discussed, whether it's shrinking the numbers with quantization, fusing operations, skipping calculations with KV caching using speculative guesses, or enabling adapter switching with ALoRA, it's all fundamentally driven by the need to tame that $1 beast and slash the enormous operational costs tied to billions of inference cycles. Efficiency isn't just about making things faster, it's the core economic driver making widespread AI adoption actually feasible.
Which brings us to our final thought, something for you, the listener, to ponder. We've seen with ALoRA that you can have dynamic, swappable skills precisely because the powerful core intelligence, the frozen base LLM, remains constant and active, while only its tiny peripheral specialization changes. Does this paradigm of fixed, powerful core with dynamically changeable, lightweight specializations suggest a different future for AI development? Maybe the focus shifts away from building one single monolithic God model that tries to do everything and moves more towards creating ecosystems. Ecosystems where shared foundational models act like operating systems and developers build thousands of small, specialized, maybe even disposable, instantly swappable adapter skills that run on top. Could the future of AI look less like one giant brain and more like a powerful core surrounded by a constantly changing swarm of hyper-specialized tools?